Hello, my name is Catherine Knox, and I'm presenting to you the final project for Time Series Analysis Spring of 2025 project entitled United States Monthly Electricity Generation Modeling. The goal of the project is to create time series models in order to make forecasts for future electricity generation in the United States. This forecast framework can be used as a baseline for budgeting resources and is also a useful resource in future government strategic initiatives, such as infrastructure. For a description of the data was retrieved and is publicly available at two government websites. It was monthly data from January of 2022 to November of 2024, with the last 6 months exclusively used to test the models for their accuracy. The two sets of data are total net electricity generation from all sectors for the United States, so basically electricity usage in the United States. And the second set of data is, for the same time period, the average monthly surface temperature of the contiguous United States. The different time series models that will be used in this project are vector autoregression, and I'll go into a little bit more detail later on, but the features are going to change a little bit in different VAR models, and the LSTM, long short-term memory. Both of these models are useful when multiple predictor variables are present. R is used in this project for the data analysis, manipulation, models, and plotting, and Shiny in R is used for the application. So let's take a look at the application. Basically, it's showing the time plots over time first for electricity. You can see the seasonality and increasing trend. Temperature, obviously, there's seasonality. No noticeable trend that we can see with our eyes for this one. This next chart is very interesting in that it's U-shaped, so the regression line doesn't follow it very well. But you can see as the temperature extremes, extremely low and extremely high, more electricity is needed during those times. So in order to split that out into two functions, we split it into heating degree days and cooling degree days, defining them as a delineating point of 65 degrees or over would be cooling degree days, and under 65 degree days would be heating degree days. So you can see as the temperature or as the stress increases for the temperature extremes, more electricity is needed in these two instances. However, it's much more distinct and rapid in the cooling degree days, probably because electricity is used exclusively for cooling, whereas heating uses other heat sources or other sources. As far as the decomposition models, you can look at those in the app. Electricity has seasonality and a trend, so does temperature, and HDD and CDD both have seasonality with some interesting trends there, which basically, as you compare year over year, some summers and some winters are warmer or cooler than others. As we look at the model, so in these charts, you can see the confidence interval in purple, the forecast in blue, and the actual values for the test data set in red. So you can see that the VAR with the temperature did pretty well. It stayed within the confidence interval. I was hoping that the HDD CDD distinction would improve the model, but it didn't seem to do that. It was very similar, almost exactly the same as far as results, root mean squared error. And it did fall within the confidence interval, but moved toward the edges in quite a few places. The TSLM model, however, followed very closely with the actual data. And it was definitely the best model as far as root mean squared error and accuracy. Also of note is this model required a feature input for the forecast. So we inputted the temperature during this time frame to generate an electricity forecast. So as you can see, knowing the temperature data during a time frame can really help you create a model and an accurate forecast for electricity usage. I hope you enjoyed this presentation. Thank you very much.